Hello everyone. Today I'm going to discuss a familiar topic from data structure and related to graph. The problem is that suppose a graph is given, so we can traverse the graph and it can be traversed in two different ways, either DFS or BFS. The full form of DFS is depth first search and full form of BFS is breadth first search. So in this video we will see the problem on depth first search. Suppose a graph is given. So find out DFS traversal order. Find out DFS traversal order for the given graph, and draw the corresponding DFS spanning tree and draw the corresponding DFS spanning tree. So, what is the full form of DFS? The full form of DFS is depth first search. So, to illustrate this procedure, we will use a third data structure, which is stack. Already, most of us know about the stack data structure. Only insertion and deletion, these two operations are permissible onto stack. The insertion into stack is known as push operation and deletion from the stack is known as swap operation. But here is one point: insertion and deletion should be done from only one end of the stack, which is known as top. From the topmost insertion, the new item to be inserted as the topmost element into the stack, and the item to be deleted should be the topmost element of the stack. So only one end, the insertion and deletion can be done, and that is the topmost element. Either topmost element will be deleted or new item to be inserted as topmost item into the stack. So do this DFS traversing, you have to use a data structure which is called stack. So to illustrate this problem, we will take help of an example, and for that particular example we will see how this traversing is done. Traversing is vertices in the order, in which order? According to depth first search order. So according to that order, the graph will be traversed. So I have to write the sequence of vertices in the which will be the depth first traversing order, the sequence of vertices, and the corresponding depth first search spanning tree to be drawn. To illustrate this particular problem, we are taking help of a particular example. The example is, this is the vertices A, B, S, I, C, D, E, then F, then G, then H. These are the vertices, and how these vertices are connected. Now the graph is like this. There is the path from A to B and B west. Then I'm just drawing the graph by connecting the vertices according to the edges of it. And this is the graph. So in which order the vertices will be traversed? We will follow the depth first search technique for traversing the vertices, and the corresponding vertex sequence, which is known as depth first traversal order, which is known as depth first traversal order. That means a sequence of vertices that we have to find out, and we have to draw the corresponding depth first spanning tree. To draw the depth first spanning tree, we will first write the vertices, and according to the traversing, the edges will be connected. So I'm drawing the vertices only once again for drawing so that it will be a depth first spanning tree. Okay. C, D, E, F, G, and H. Now, I have to use a stack, and I have already told you that only two operations on the stack are possible. One is push and other is pop. When there is a push operation into the stack, that means a new vertex to be inserted into the stack as the topmost element, and that will come to this depth first traversal order, that vertex. And when there is a push operation, then there will means we are moving forward from a particular vertex to that next vertex. That when there is a pop operation, that means we will not move forward, rather we will move backward from current vertex to previous vertex. That is related, how push and pop operation is related to that DFS traversing. In DFS traversing, first we will take a vertex, and we will move forward from that vertex to the next vertex. If there is a push operation, then we will move forward to the next vertex. But if there is a pop operation, then we will backtrack from the current vertex towards previous vertex. So this is the push and pop operation and the corresponding traversing of the vertices. So first, I will start from the vertex A. Okay. So the first operation we will do is push A. Push A. So when a push operation is done onto the stack. So initially the stack is empty. Now stack will contain only this vertex, that is vertex A. So when there is a push operation, so what is the changes in this graph we have to do? When there is a push operation, then the vertex which is pushed into the stack, that is obviously will be a topmost element. As the initially stack was empty, so A becomes a topmost element, and then vertex sequence we have to write the item, that means A, which we have just pushed into the stack. And as we have pushed that vertex into the stack, that means we have visited the vertex. So it will be, this vertex will be marked as visited. So we make a cross here. So then there will be next push operation. But in this next push operation, which vertex will be pushed into the stack? We have to take the unvisited neighbor vertex of A. From this graph, so the next push operation will be what? An unvisited neighbor of A. An unvisited neighbor of A. Now we have to see this graph. See, the A has two neighbors only, that means adjacent vertices B and A, and both are unvisited. When they are crossed, that means they are visited. But we have not visited any of the neighbor vertex, so we can take any one of them. For this example, we take the next vertex, neighbor vertex of A, which will be pushed into the stack. Let it be S. So what we will do? The operation will be push S. So when this operation is being done, so there will be changes into the stack. S will be pushed as the topmost element of the stack. Previously, the content of the stack, there was only A. So now S will be the topmost element. That means it has been inserted into the stack. So what will be the changes in here in this first traversal order? The next vertex that will be traversed is will be is. So is will be indicated as visited vertex, so we make a cross here. And in this depth first, what will be the changes in depth first spanning tree? An unvisited neighbor of A is S. So there will be, when there is a push operation, we will move from A to S. That means from A to the top of every item. Move from in black out. With yeah. Okay, so an unvisited neighbor of A is S. So what we are doing, we are moving forward from A to S. Here there will be a path from A to S. Next operation obviously will be a push operation, and that will be related to the the push operation will be on the current topmost element of the stack, which is S. The next operation is push on unvisited member of S. So for that we have to see this graph. Now from this graph only there is three neighbor vertices of S, which is C, G and I, and all of them are unvisited. So let we take any one of the unvisited neighbor of S, let it be C. So that now C will be inserted into the stack as a topmost element. So the next operation will be push C. So then what will be the changes in the content of the stack? Previously it was A, if that was the previous content of the stack. Now C has been inserted as a topmost element into the stack. And when C has been inserted, what we have done, we have pushed a neighbor vertex of S, and the neighbor vertex is C. So there is a push operation. So in the first spanning tree, we will move forward from S to C. So we connect this path S to C. That means we are moving from S to C. And as C has been inserted or pushed into the stack, this vertex is visited, so we make a cross here. The next push operation will be on the topmost element of the stack, which is C. So the next operation is push on unvisited neighbor, push on unvisited neighbor of C. So for that we have to see the graph. For C, there are three neighbors, G, E and J, and all of them are unvisited. So we can pick any one of them to push into the stack. So for example, we are taking the vertex C to be pushed as an unvisited neighbor of the stack, unvisited neighbor of C, that is to be pushed into the stack. So what we are doing, we are doing push operation, and it is E. So what will be the changes in the content of the stack? Previously the stack was this, now the content of the stack is this. So as we have pushed vertex E into the stack, so this vertex is marked as visited. And we are doing this push operation and it is from C to E. That means in this first spanning tree, there will be a movement from C to E. So we will connect C to E. So there is a movement from C to E. Now, the topmost element of the stack is E. So we will do push operation for this topmost element. So what the operation will be? It will be push and unvisited, push and unvisited member of E. So we have to find out the graph here. Is there any unvisited neighbor of E? Yes. There is only one unvisited neighbor of E, which is H. So we will push H onto the stack as the topmost element. So the operation will be push H. So what will be the change in the content of the stack? Previously the stack was this, A is CE. Now H has been inserted and it is the topmost element. Now as the vertex A has been inserted into the stack, so this vertex H is now visited, so we mark H as visited. And what will be the change in the corresponding DFS spanning tree? Now, this is a push operation from E to H. So there will be a movement from E to H in the traversal spanning tree construction procedure. So there will be an H from E to H, and so we move from E to H. So now the topmost element of the stack is H. So we will do push operation. So what will be that operation? Push and unvisited member of H. So if there is any unvisited member of H, so we see the graph. There is only one unvisited neighbor of H, that is G. So G will be pushed into the stack and it will be the current topmost element of the stack. So the operation push an unvisited neighbor of H means push G. So what will be the changes in the content of the stack? Previously it was A, S, E, E, H. Now G is the topmost element into the stack. As the vertex G has been inserted into the stack, so this vertex has been visited, we mark it as visited. And as this is a push operation from H to G, so in this spanning tree, there will be a movement from H to G. So we connect these two vertices by an H, and there is a movement from H to G. Now the current topmost element of the stack is G. So push operation will be performed related to the topmost element, that means related to G. So what will be the operation? Push and unvisited neighbor, push an unvisited member of G. So is there any unvisited member of G? For that you have to see the graph. For G there is only one unvisited member, which is F. So F should be pushed into the stack. And so the operation will be then push F. So F now will be the current topmost element of the stack. So previously stack content was A is C, E, H, C. Now has been inserted. Now it is the topmost element. As the vertex if has been inserted into the stack, so this vertex is visited and we mark it. And there is a movement from G to F. So in this first spanning tree, they will move forward from G to F. So there is a movement from G to F. That is, we are moving forward from the current vertex to G to its next vertex, which is neighbor of G, that is F. Now, the topmost element of the stack, current topmost element of the stack is F. So we have to do the push operation related to F. So what we will do? The next operation will be push and unvisited neighbor of F. Is there any unvisited neighbor of F? If see the graph, see for if the neighbors are C and G and both are visited. So there is no unvisited neighbor of F. So from F we cannot move forward. So what is the operation? We have to do the pop operation now. So there is no unvisited neighbor of F, none. So what the operation will be done? The operation will be pop. Pop means the topmost element of the stack will be deleted. So what will be the current stack item? Oh, just a minute. Here one thing in DFS traversal order, whenever there is a push operation and the item that is being pushed, that is being written in the sequence, and that will be the DFS traversal order. So what we have done, we have written up to S, that when push A, then push S, then push C. So C will come here, then push E. So E will come after C. Next operation was push H. So H will come after E. After H there is a push operation of G. So G will come here. So after G there is a push operation of F. So F will come in this sequence. Now after push F there is a pop operation. Pop operation means the topmost element, that means F, will be deleted from the stack. So the current stack item will be A, S, C, E, H, and E. And remember, when there is a pop operation, that means there is a backtrack. In this DFS spanning tree, there will be the backtrack operation from F to which item? From F to G, which is the current topmost element. So from F to G, we have the current vertex was F, and we will now backtrack from F to G. So there is a movement from F to G, backtrack movement. So what is the current topmost element of the stack, which is G? So push operation will be related to this topmost element G. So what I am doing? The next operation will be push and unvisited neighbors of G. So is there any unvisited neighbor of G? So we see the graph, there is neighbor of G are S, F, H, all are visited. So there is no such unvisited neighbor of G, none. So the operation will be on the stack will be pop operation. That means topmost element of the stack will be deleted. So the last stack content was like this. So now the stack becomes A, S, C, E, and C. And as there is a pop operation from G2, so there will be a pop operation in depth spanning tree, there will be a backtrack, which is from G to topmost element item, which is H. So from G to H in depth spanning tree, there will be a movement backtrack from G to H. Now the stack's topmost element is H. So we will do the push operation related to the current topmost element of the stack, that is H. So what we will do, we will push an unvisited neighbor, push an unvisited neighbor of H. So now we have to see the graph. Is there any unvisited neighbor of H? No. The neighbor of H are G and P, and both are visited. So no such unvisited neighbor of G, none. So the operation will be pop operation onto the stack. That means in this first spanning tree there will be a backtrack operation. So in stack there will be a pop operation. So previously stack was this, now H will be removed from the stack, and now the content of the stack will be A, S, C, E. As it is a pop operation, so in the first spanning tree, there will be a backward movement, and which is from H to E, which is now E is the now topmost element. So there will be a backtrack movement from H to E. So we do this backtracking. So now the topmost element is E, and I have to do the stack operation related to this topmost element. So what operation we will do? Push an unvisited member of C. So is there any unvisited neighbor of E? C. Here E has only two neighbors, C and H, and both are visited. So there is no such unvisited neighbor. So the operation will be, so what's the operation? The operation will be pop. That means the topmost element of the stack, which is E, that will be removed, and the current stack content will be A, S, C. As there is a pop operation, so we will not move forwards from the current vertex, rather we will move backwards from the current vertex. So current vertex is E. So from E to C, the topmost element of the stack is now C. So from E to C there is a movement, that is a backtrack movement from current vertex E to its previous vertex, which is C. So this is a backtrack movement. Now the topmost element of the stack is C. So operation will be related to this topmost element. So next operation is push an unvisited neighbor, push an unvisited neighbor of C. So if we see the graph here, is there any unvisited neighbor of C? C has neighbors D, E, F and S. Among these, only D is unvisited neighbor. Yes. So what we will do? We will push this unvisited neighbor D, which is unvisited neighbor of C. That will be inserted into the stack. So the next element will be pushed into the stack is push D. So what will be the change in the content of the stack? Previous stack content was A, S, C. Now D becomes the topmost element. So in DFS traversal order, as it is D has been pushed, in DFS traversal order the next vertex sequence will be D. And as D vertex D will be marked as visited. And what will be the change in state first spanning tree? As it is a push operation, so from C to D, so there will be the forward movement from C to D in depth of spanning tree. So we will connect this path C to D, and this is the forward movement from C to D. Now the topmost element of the stack is D, so we have to do the operation related to D. So what we will do, we will do push and unvisited neighbor of D. See the graph. D has only one neighbor C, which is already visited. So we cannot move forward. So there is no such unvisited neighbor none. So there will be pop operation into the stack. So the topmost element of the stack will be deleted. So previously the content of the stack was D, now it will contain only A, S, C. It will be deleted. So A, S, C. That will be the current content of the stack. And as it is a pop operation, so there will be a backtrack movement from current vertex D to its previous vertex, which is C. So there is a backtrack movement from D to C. There is a backtrack movement. Now the current vertex is C, okay? That is the topmost element. Now we have to do the push operation. Is there any unvisited neighbor of C? An unvisited neighbor of C. See the diagram. There is only three neighbors, S, E, and F of C, which are neighbor of C, but all are visited. So there is no such unvisited neighbor of C. So the operation will be pop. So the operation will be pop. So the content of the stack will be only A and S. We will be removed. As there is a pop operation, so in this first spanning tree, there will be a backward movement from the current vertex C to S. So there is a backtrack movement from current vertex C to vertex S, to its previous vertex, which is S. Now the operation will be related onto this topmost element, that is C, which is the current vertex. So what we will do here, the next operation is push and unvisited neighbors of S. So you have to see the graph here. See the graph has so many vertices A, C, D, and I. Among them, only I is unvisited neighbor of S. So the operation will be push operation, and the vertex I will be inserted into the stack. So it will be push I. So when there is push I, so what will be the change in the content of the stack? Before the content was AS, now I is inserted as the topmost element. So in this first traversal order, the next vertex sequence will be I. And as this vertex has been pushed into the stack, so we mark it visited. And in this first spanning tree, there is a forward movement from S to I. So what we will do, this is connected S to I. That means there is a forward movement from S to I. Forward movement means we are going to visit a new vertex, and backward means we have already visited that vertex, and which was visited just prior to the current vertex. Okay. Now the topmost element is I. So the push operation will be on I. So push push unvisited neighbors, push unvisited neighbor of I. You could see the diagram. There were no unvisited neighbor of I. So no such vertex, none. So there will be a pop operation. So the topmost elements of the stack will be removed. The I will be removed and the current content will be A and S. So as there is a pop operation, that means we cannot move forward to the new vertex from I. Rather, we will move backward from I to S, which is the current topmost element of the stack. So there is a backward movement from I to S. Okay. Now the push operation will be related to this topmost element S. So push, so there will be push unvisited member of S. So we have to see the graph, whether is there any unvisited member of S or not. So this promise there are no such unvisited neighbors. So no such unvisited neighbor, none. So what operation will be performed? It will be pop operation. So the content of the stack is that S will be removed from the stack. Now only A is the element into the stack. As this is a pop operation, so there will be a backward movement from current vertex to its previous vertex. Current vertex is S and the previous vertex of S was A. So there will be a backward movement from S to A. So in this first spanning tree, there will be a backward movement from S to A. Now the A is the topmost element of the stack. So push operation will be related to this vertex. So what we will try, we will do push unvisited members of A. If we see the graph, for A there are two vertices B and S, only two members, and among them B is the only unvisited member. So we will insert it, we will push vertex B into the stack. So the next operation will be push B. So the current content of the stack will be A and B will be topmost element of the stack. So B has been pushed into the stack. So in this first traversal order, the sequence of vertex, the next vertex will be B here. As B has been pushed into the stack, so we will mark this B as visited. As it is a push operation from current vertex A to B, so in this first spanning tree, there will be a forward movement. That means we are going to traverse a new vertex from the current vertex. That means we are going, there is a movement from A to B. So we connect this edge with AB. And there is a forward movement from A to B. So now the stack content is this. So what will be the operation? That will be related to the topmost element B. So push and unvisited neighbor of B. You have to see the graph whether there is any unvisited member of B. See here, B has no unvisited member. So no such vertex, none. So the operation will be performed as pop. So the current status of the stack, there will be only A. B will be deleted from the stack, and as there is a pop operation, so there will be a backward movement from the current vertex B to its previous vertex, that is A. So in this first third spanning tree. The current vertex was B, and now we will do backtrack to previous vertex, which is B. So there is a backtrack movement from B to A. Now, whatever the operation that will be related to this topmost element of the stack, which is A. So what we have to do, the operation will be push an unvisited member of A. See the diagram, see the graph here. See, in this A, there is no such unvisited neighbor. So no such unvisited neighbor. So what will we do? We will do the pop operation, and the topmost element of the stack will be removed. Now the stack becomes empty. So when the stack becomes empty, that means all of the vertices have been traversed. So we stop our depth first traversal. And after stopping, here we find out the depth first traversal order, which is the sequence of this vertex. This is known as the depth first traversal order, and this becomes the depth first spanning tree. If we just remove this arrow, that is for understanding purpose, make it clearly how the movement is being done. So that's why I have given this direction of movement. But now, if you want to draw the tree only, that means the vertices and their edges only, then the tree will look like this. So what will be the content of the tree? So first of all, we have to draw the vertices A, B, S, C, D, E, F, G, H, and I. And according to this, if we see this traversing order, okay, there is an edge between A to B, then A to H to C, C to D, C to E, C to H to G, G to F, H to I. So that is just the first spanning trees for this particular given graph. Now you can see the difference between this graph and between this depth first spanning tree. In this tree there is no loop, but in graph there is a loop. But while we are drawing this tree, we are including all the vertices of the given graph, but the edges are minimal without any loop. So as this is the tree is drawn according to depth first traversing sequence of vertices, so that's why this spanning tree is called GFS spanning tree. And the spanning and this order sequence of vertices will be this. Okay.